Assalamu alaikum. Hello everyone. This is GOUASMIA Takrim speaking. I am PhD student at GOUASMIA University, and today I am going to present on the behalf of me and my co-authors our work submitted for participating in the first international conference on chemical matters and environment preservation organized by the University of Ouargla, which is titled XRD Investigation of Mechanically Alloyed Iron-Based Ternary Powders. This presentation will include an introduction, an experimental part, result and discussion, and a conclusion. Well, the ternary iron-nickel-cobalt system is one of the nano-combinations with high-quality magnetic properties. Such alloys have a high saturation magnetization and a low coercivity, which allow them to be used efficiently in high-density magnetic recording media. Many studies have been conducted to investigate the significant properties of iron-nickel-cobalt alloys produced via a variety of techniques such as mechanical alloying, sol gel, thin films ultrasonic irradiation, and so on. Therefore, the aim of our work is to investigate a variety of ternary iron cobalt nickel samples produced with the technique of mechanical alloying and analyzed using the X-ray diffraction technique. For the experimental part, the iron, cobalt, and nickel element powders with high purity were milled to form iron 50 cobalt 40 nickel 10 system in a fridge pulverized 7 planetary ball mill. To prevent oxidation from contaminating the powder, the vial was sealed in an argon atmosphere. The milling process, on the other hand, was designed to pause for 15 minutes every 30 minutes to avoid the overheating inside the jar. The mechanical alloying was performed over several periods, up to 48 hours, in order to track the formation of the nanocrystalline structure. We used the X-ray diffraction technique to examine the phase evolution and the structural parameters of the alloyed samples as function of milling time. Those parameters were revealed via the refined X-ray diffraction data by the Rietveld refinement using the mode program version 2.99 as it is shown in figure 2. We start the part of result and discussion with the X-ray diffraction spectrum of the annealed powders shown in figure 3 that reveals all the expected starting element peaks. As it is shown, the non-alloyed sample is composed of iron with a body-centered cubic structure, nickel with a face-centered cubic structure, and cobalt with two allotropic structures, face-centered cubic and hexagonal close-packed. The iron BBC phase possesses 5 main peaks with high intensities and narrow widths, while the minor peaks correspond to cobalt and nickel. In this beginning mixture, the three phases have overlapping peaks. As it was established by the X-ray diffraction analysis that iron cobalt nickel BCC solid solution has been formed after 48 hours of mining. This new phase was promoted by the division of cobalt and nickel atoms in toward the BCC iron structure. Only peaks belonging to the iron BCC structure can be identified as the milling time increases up to 48 hours, confirming the formation of the solid solution inside the iron matrix. The proportions of the new phase solid solution increases from 43.64% after 1 hour of mining to 100% after 48 hours of mining, becoming the only and the total phase existing. Here we can see the typical refined X-ray diffraction pattern of the mixture iron 50, cobalt 40, nickel 10, fitted by the mode program using the Rietveld method before mining and after 48 hours of mining. The refinement results confirm the formation of the body-centered cubic iron cobalt nickel solid solution. It was also noted that the proportion of the hexagonal cobalt and the face-centered cobalt phases manifest with an opposite trend. However, both phases disappear totally above 6 hours of mining. The observed anisotropic change in the proportion of the cobalt phases can be associated mainly to the dissolution of cobalt within the iron host lattice and to the allotropic phase transformation of cobalt from the face-centered cubic form to the hexagonal form or vice versa. It was also found that at ambient temperature the cobalt face-centered cubic phase is metastable, but it becomes unstable when it is subjected to mechanical or thermal energy. Thus, the atoms of cobalt face-centered cubic phase diffuse toward the cobalt hexagonal phase due to the high energy generated through milling. Figure 7 depicts the average crystallite size and the microstrain rate of samples. The amilled iron cobalt nickel mixture had a crystallite size of around 121 nanometer. A notable sharp decrease to 60 nanometer after 1 hour of milling is shown, which is primarily due to the formation of a new solid solution. Between 1 and 3 hours of mining, there is almost no change in the crystallite size. As a result of subdividing the layered nanostructure regions through rotation of the equiaxed regions, the crystallite size continues to decrease from 29 nanometers to 9 nanometers between 6 and 24 hours. The obtained minimum grain size after 48 hours is thought to be the result of a balance between the formation of dislocation structures and their recovery by thermal process. On the other hand, the variation of the microstrain rate with milling time indicates that mechanical alloying causes significant lattice straining. The incorporation of both cobalt and nickel into the iron matrix results in a significant increase in the microstrain rate, as it is expected. During the deformation process, it rapidly rises and reaches a maximum for longer milling time. In fact, this increment of strain is mainly due to the large density of dislocations generated by the severe plastic deformation of highly active nanoparticles that exhibit an anisotropic behavior. The attained maximum strain level can be justified by the transition of the deformation process from plastic deformation via the formation and movement of dislocation to the sliding of the grain's boundary. Figure 8 shows the change in the lattice parameter of the milled iron 50 cobalt 40 nickel 10 alloy powders with milling time. The change in the lattice parameter indicates that the milling process has produced an atomic disorder. Before milling, the lattice parameter of the iron BCC structure was 0.2866 nanometers. After 6 hours of milling, a rapid decrease in the lattice parameter is observed. With prolonged milling time, the lattice parameter continues to decrease, reaching a minimum value of 0.2855 nanometers at 48 hours of milling. The decrease in lattice parameter between 6 and 48 hours can be explained by the highly diffusivity of cobalt and nickel through the disordered iron matrix. In addition, this reduction may be attributed to particle compression, which is due to the presence of compressive stress fields in the non-equilibrium boundaries within the microcrystals. Finally, as a conclusion, we can say that with increasing milling time, the cobalt and nickel peaks gradually decrease, while those of iron remain present, resulting in the formation of a nanostructured iron cobalt nickel solid solution with a body-centered cubic. The average crystalline size of the nanostructural alloys decreases with mining time, reaching 8.17 nanometers after 48 hours. Meanwhile, the rate of the microdeformation rises up to 0.56%. And the introduction of the plastic deformation by mechanical alloying and the diffusion between elements were both factors in the alloy formation. As a result, a large number of dislocation and grain boundaries were created, causing the lattice parameter to be disordered. Thanks for your attention and stay safe, please.